15.1 Friction. Anytime two surfaces rub against each other, there will be friction. At the microscopic level, this is due to the irregularities in the two surfaces rubbing against each other. For a moving object, friction is always in the opposite direction to the direction of its movement. There are two things that can change the amount of friction on an object. The amount of friction depends on the types of surfaces involved. Different surfaces have different levels of roughness. But they also have a different level of lubrication. For example, wet cement has less friction than dry cement. Friction also depends on how much the two surfaces are pushing against each other. If they're pressing against each other harder, irregularities in the surfaces have more ability to catch on each other, so there should be more friction. The types of surfaces involved are given mathematically by a number we call the coefficient of friction. This is given by Greek letter mu, which is a U with a tail on each side. We call this the coefficient of friction. Coefficient of friction is a number that indicates the stickiness of the surface involved. For example, rubber would have a much higher coefficient of friction than ice. How much the surfaces are pushing against each other depends on the normal force. Remember, the normal force is the force of how much the surface pushes back on the object against gravity. So it's a very good indicator of how much the two surfaces are pushing together. Before we go and look at formulas for friction, let's start by really looking at the coefficient of friction. This is given by Greek letter mu, which, as I said before, is a letter U but with a tail on both sides. The coefficient of friction has no units. It's just a number. And it is unique for every surface and every surface combination. Rubber on ice has different friction than wood on ice or aluminum on ice. So we would find a different coefficient of friction for each surface. It's also important to know that coefficient of friction comes in two types for each combination of surfaces. The first is static friction. Static in physics means not moving, like static electricity refers to electricity that's staying still. Static friction is how much force is required to get an object moving when it's at rest. So an object that's not moving can still experience friction. You can push against it, and it's hard to push because friction pushes back. The other type of friction is kinetic friction. This is the friction an object experiences when it's already moving. It's how much friction the object experiences while moving. Here's a table that shows some coefficients of friction. Mu static is given by a mu little s, and the kinetic coefficient of friction is given by mu little k. Static friction, as you can see on the table, is always greater than kinetic friction. It is harder to get an object moving than to keep it moving once it's already going. Sort of like some of my students in the morning when they're trying to get out of bed, I'm sure. The formula for friction involves both the normal force and the coefficient of friction. Force of friction equals mu, which is the coefficient of friction, times the normal force. The coefficient of friction is just a number that tells you how sticky the surface is. Every combination of surfaces has to be tested differently to find out its coefficient of friction. So you'll usually find these on tables or given in problems. You'll sometimes have to find it yourself, assuming that you already have enough information to solve for it. But usually the coefficient of friction will be given. The normal force is how much the surfaces are pushing together. Here's an example. What force must be applied to get a 10-kilogram wood block moving on a wood floor? To solve this problem, we need the coefficient of friction for wood on wood. The coefficient of static friction for wood on wood is 0.40. The coefficient for kinetic friction on wood is 0.20. We start these problems by drawing a free body diagram so we can assess the forces involved in order to make sure we have an accurate understanding of the normal force. The force of gravity and the normal force are directly opposite each other, and there's no other vertical forces. For this reason, we can be sure that the normal force is equal to the force of gravity. To move the block, the applied force must be greater than the force of static friction. The force of static friction has a maximum value at the coefficient of static friction times the normal force. If the force can be just a little bit greater than this, it will get the object moving. So this is the minimum applied force. The normal force is equal to the negative of the force of gravity, which is negative 10 times negative 9.81, which gives us positive 98.1 newtons. The force of friction static is mu static times Fn, which is 0.40 times 98.1, which gives us a friction static at a maximum value of 39. So if the applied force can be 39 newtons or greater, the object will be moving. This is the force that must be overcome by the applied force to get the object moving. Here's another example also using the same block on wood on wood. Once the 10 kilogram wood block is moving, the applied force continues to be applied for 5.5 seconds. How far does it travel? It's important to realize that the block is moving now, and for this reason we use the kinetic friction. Once a block is moving, there is much less friction. So friction decreases, and we're able to get a little bit more net force. So now the 10 kilogram block is being pulled down by gravity, pushed up by the same normal force as gravity. There's an applied force equal to 39 newtons pulling it, and there's a force of kinetic friction pulling it back. Let's calculate what the force of kinetic friction is. The normal force has not changed. It's still the same object on the same surface, but kinetic friction is now 0.20 times normal force, which is 98.1, giving us a force of kinetic friction equal to 19.62 newtons. The net force is equal to the applied force minus the force of kinetic friction. This is 39 minus 19.62, which is, just by fluke of the numbers, 19.62 newtons. We can use this net force to find the acceleration of the block. Acceleration is F net divided by mass, which is 10, which is 19.62, divided by 10, which is 1.962 meters per second squared. Finally, we can use this acceleration to find out how far it travels. We know from earlier in Physics 20 that the distance equals VIT plus 1/2 AT squared for an accelerating object. Since the object was originally at rest, VI is 0, T is 5.5, and we just calculated the acceleration to be 1.962. So the distance is 1/2, 1.962 times 5.5 squared is 30 meters. One of the things students find difficult about friction is determining the normal force, because there's no clear formula for normal force. This is on purpose. Normal force depends on the situation. Usually, normal force and force of gravity are balanced. And since they balance each other, we know that the normal force equals negative the force of gravity, which is mass times 9.81. There are some exceptions to this, however, and that's why there's no clear formula. The first exception is when you have an object being pulled by an applied force, and that applied force is at an angle. If the applied force is at an angle, there's a vertical component to this applied force that is either contributing to the normal force or taking away from the normal force. So the normal force is not just equal to force of gravity, there's another piece. The second time when normal force does not just equal gravity is when an object is on an inclined plane. In this case, the normal force and force of gravity are at angles to each other, so they can't be perfectly equal. We'll look at inclined plane in the next lesson, but for this lesson, let's look at an example where the applied force is at an angle. A 15 kilogram suitcase is pulled with applied force of 100 newtons at an angle of 60 degrees above the horizontal. How much does the suitcase accelerate if the coefficient of friction is 0.150? For these problems, it's quite useful to always draw a free body diagram to try to visualize the forces involved in the situation. So we have our 15 kilogram suitcase, and it's being pulled at an angle by 100 Newton force. Friction is pulling it back, gravity pulls it down, and there is some normal force, we don't know what it is, keeping it from falling through the surface that it's settled on. We'll start by breaking the 100 Newton force down. This 100 Newton force is at an angle of 60 degrees. And for this reason, we recognize that it can be broken down into an x component, which is horizontal, and a y component, which is vertical. We'll call the x component F applied x, or FAX, which is 100 cos 60 because the x is adjacent to the 60. FAY is 100 sine 60 because y is opposite to 60. And to solve for the normal force, we need to look only at the y forces on the suitcase. The suitcase is being pulled down by gravity, but there are two upward forces in the y direction, the normal force and F applied in the y direction. Now we know that the net force in the y direction has to be 0 because the suitcase isn't sliding through the floor or floating up. So 0 equals normal force plus FAY plus FG, the combination of all vertical forces. 0 equals Fn plus 100 sine 60, which is FAY, plus 15, which is the mass, times negative 9.81, which is the acceleration due to gravity. 0 equals Fn plus, the combination of the other two numbers is 86.6025 minus 147.15. If we solve for Fn, we find that Fn equals positive 60.547459 newtons. We can use this normal force to find the force of gravity pulling on the suitcase. The force of friction pulling on the suitcase. Force of friction is equal to the coefficient of friction, which is 0.15 times this normal force we just calculated, 60.547459. The force of friction is 9.0821189 newtons. Now we look at the x forces on the suitcase only. We know that the suitcase will accelerate in the x direction because there is an applied force in the x direction and only a little bit of friction holding it back. The net force in the x direction will be this applied force in the x direction minus the force of friction. The applied force in the x direction is 100 cos 60 minus the force of friction, which is 9.0821189 newtons. This gives us an F net on the suitcase of 40.917881 newtons. And we can calculate acceleration by dividing the F net by the mass of the suitcase, which is 40.917881 divided by 15 kilograms. This gives us an acceleration of 2.73 meters per second squared.